this particular problem is, I think, a good one to start with. You've probably seen this before. So you have a ball. So say this is a hollow sphere. It's rolling down the side of a hill. It starts at point A. That's some height, capital H, above the ground, and it rolls down, gets to point B. B to C is smooth, so there is no friction here. And then from C it climbs up another hill because it has some speed, right? It's moving, so it's going to start climbing and gets to some point D, where it momentarily stops climbing and then turns back. We're not worried about what happens after it turns back. We only really want to see how high it climbs on the slope CD. So, any ideas on how to tackle this? How would you start? So by now you have, yeah. Say that again? Right, we would like to use some sort of energy conservation, right? Because that seems to be the easier thing to do. So this hollow sphere has mass m and radius r. So we know this. We know that energy is conserved. From A all the way to D. So at each point we can write down the total energy, which is going to be a sum of kinetic and potential energies. And hopefully that's enough information for us to evaluate what we need. We'll find out. Now, why is energy conserved from A to B even if there's friction? The ball is not sliding. So at the point of contact, it's not slipping. I haven't told you this, but we're going to assume this. So we're going to say in fact, we want static friction to be strong enough that it actually doesn't allow slipping at all at any point from A to B. This is somewhat counterintuitive, but this is how it works. All right. So to see how high it goes on the path CD, I want to be able to calculate how fast it is moving at point C, right? If I know how fast it's moving at C, then by energy conservation I can calculate how high it should rise up on the path CD. Now to know how fast it's moving at C, I need to know what its energy at C is. I need to know what its energy at B was, because energy at B is the same as energy at C. And to know to know how fast it's moving at B, I need to know what the energy at A is, conserve energy from A to B first. So I have to do this in a string of steps. So I'm trying to back calculate. I'm trying to see what I need, and then I'm trying to go back and figure out how to calculate this. So I'll have to start from A. So the total energy at A must be equal to the total energy at B. Okay. So say BC is ground level. So we're measuring all potential energies from, at the level of B and C. So what is the energy at A? So there's potential energy, and is there any kinetic energy at A? No, right? Right. What is the energy at B? Right. So, well, first of all, is there any potential energy? No, right? Because I'm measuring energy from, from ground level, which is BC. So if I'm measuring all potential energies from there, potential energy at B or C is actually 0. Now the question of kinetic energy, the ball is doing two kinds of motion. One is its center of mass is moving down the slope, and the other is it's spinning, right? Both have to be accounted for. So there's a center of mass kinetic energy, and then there's a rotational kinetic energy. All right. Well, I've used capital M there. Let me just change that. All right. I don't know how fast it's moving at B. I don't know how fast it's spinning at B. But can I say something about them that relates them? If I have the condition that the sphere does not slide anywhere on this track, what can I say? I can say VB is R omega B, and this happens only because I'm assuming that that the sphere does not slip on the track AB at any point. All right. I need one more thing. I need to know what the moment of inertia is for the hollow sphere. What is the moment of inertia of a hollow sphere? 2/3 mr squared. So I'm going to plug this all in. So for I have 2/3 mr squared, and for omega I have VB over R squared. We can simplify this. So the square of the fraction is the same as fraction of the squares, right? So I have half 2/3 mr squared. The 2's go away, right? Dividing and multiplying with the 2 at the same time, and this becomes VB squared over R squared. Again, I'm multiplying and dividing with R squared in the same term, so I can get rid of these. So all in all, I'm left with mgh is 1/2 mvb squared plus 1/3 mvb squared. Now remember, in this equation, what do I know, what don't I know? It's easy to get lost when you don't have numbers, right? So what I know is the mass of the sphere, I know its radius, I know height of point A. I don't know anything else. So remember what my goal was. I want to figure out how high point D is above ground level. So for that I need to conserve energy from C to D. I need to know the speed at C. If I want the speed at C, I need to know the speed at B, and that's what I'm trying to calculate here. So always keep in mind what you're trying to do. So my goal is to figure out what VB is. One thing I can do right away is I can divide both sides of the equation with m. So that will give me, and when you divide both sides, you have to divide every single term with m. So now I have GF is 1/2 VB squared plus 1/3 VB squared. I can factor out a VB squared. What is 1/2 plus 1/3? Can someone do this quickly? What is 1/2 and 1/3? Huh? 5/6. So all in all, I'm able to calculate VB is square root of 6gh over 5. So I just divide both sides with a 5, multiply both sides with a 6, and take a square root. That's for a solid sphere. For a hollow sphere, it's slightly more. You have a table. I think you don't have a table for this? Well, okay. So for a hollow sphere, the moment of inertia is 2/3 mr squared. For a solid sphere, it's 2/5 mr squared. Let me write this down. Of course, all this is assuming they're spinning about the center, right? So if you have a sphere that looks like this, they're all spinning this way. You know what the moment of inertia is for a disk, a ring? Have you seen these? Okay. Or maybe this is useful. If you have a cylinder, that's spinning about this particular axis through the center of each of the circles at the end, then you can calculate it as r half mr squared, where r is the radius of the circular part of the cylinder. All right. So now I have, going back to my problem, I have VB now. So at B, it is doing two things. It is spinning. It is also moving forward with a linear speed. So B to C. how much is the change? So what is the potential energy at B? 0. What is the potential energy at C? C must also be 0, right? Because it is at the same level as B. And they're both ground level. That's the level from which I'm measuring all heights. So potential energy is 0 at B, and this is 0 at C. And I have a combination of rotational and kinetic and rotational and linear kinetic energies. All right. If there is no potential energy change between B and C, do I expect either of the rotational speeds or the linear speeds to change? No, right? There is no energy being transferred back and forth. There is no height change. So it's going to be moving at C just the way it's moving at B. Is this okay? Anyone who's not happy with this? All right. So omega C is the same as omega B. And the linear speed at B is the same as linear speed at C is the same as the linear speed at B. All right. So now we come to the final stretch. We want to see how high the ball goes up on the track CD. So I know the energy at C must be equal to the energy at D. What is the energy at C? There is no potential energy. There is some kinetic energy, which is the same as the kinetic energy at B, right? So this is the same as half mvb squared plus half I omega B squared. What is the energy at D? Now, if D is the maximum point up to which the ball travels, what should its speed be? 0, right? If it had any more, well, I'm talking about linear speed. If I throw a ball up at its topmost point, the speed is 0. Why? Because if it had a little more speed, it would go even further up. And that would be its topmost point. So right at the top of its journey at D, the linear speed must be 0. Of course, why is it slowing down? Because it's gaining potential energy, right? It's climbing up a hill, so it has to slow down. So there's a potential energy that it gains. Now I don't know what this small h is. That's what I wish to calculate. But I know that if I knew small h, this is what it is. Am I missing anything else? Am I missing anything else? All the way at the top. There's no friction from C to D, right? So does the ball keep spinning at D or does it not spin at D? Say that again. Speak up. It keeps spinning. There is okay. Think about it like this. From A to B, if I didn't have friction, would the ball be spinning at point B? if I take a bowling ball, right, I go to a slope, it's very slippery, it's an icy slope. I take the ball and I let it go. Is the ball going to spin very well? It's not, right? It's just going to slide. For there to be some interaction between the spinning part and the forward motion of an object, there has to be friction. If you don't have friction, for instance, you're driving, let's say, and has anyone ever been to a hilly city? I drive in Pittsburgh every now and then. Horrible roads. Oh my goodness. They have really hilly roads, and they have these annoying stop signs just at the top of hills and at the bottom of hills. Most amazing way to get someone into an accident. Most spectacular way to do it. If you ever have driven on hilly, in hilly regions and in icy conditions, you will know that even as your car slows down, your wheels can keep spinning, right? Can you imagine this? Even if you haven't driven, you should be able to imagine this. So from C to D, if I don't have any friction at all, see, the ball is slowing down in terms of how fast it's going forward, but it's still spinning. So it starts spinning here, it goes up, it keeps spinning, and then as it spins, it comes back down. So there is no rotational energy at the top. Oh, sorry, there is exactly the same amount of rotational energy at the top as there is at the bottom, which is exactly half I omega b squared. That energy is trapped. That energy is trapped inside the rotational part of your system, and it's not available for conversion to potential energy. Just because you have that energy does not mean it's available. Right? So you have same terms on both sides of the equation, so ultimately I can get rid of these. Subtract half I omega squared from both sides. So what I'm left with is the fact that any potential energy gain must come purely from the linear part of the motion, not from the rotational part. So I know VB is 6gh over 5. So again, I can get rid of g from both sides. This will be a 3, so I have h's. It only goes up 3/5 of the way. It doesn't go up all the way to the height that A is at. All right. I think this is a good problem, I think, for a variety of reasons. It forces you to think about energy conservation. It forces you to think about, you can, for practice, you can redo the same problem with a solid sphere. What difference does that make, right? You can do it with a disk. You can do it with a ring, a hollow cylinder, what have you. So try it out with different moments of inertia, just to work through it, just to get a feel for how the physics works. But for now, we'll move on, and we'll talk about work done in rotational motion very briefly. So consider a situation you know what, let's do another problem. Since we're doing problems, let's do another problem. let's do a problem on statics. So say I have a beam, okay. I've hinged it at the wall. Now if I just let this beam go, it's gonna swing and crash, right? So I don't want that to happen. I want this to be supported. I mean, presumably it's going to hold, I'm going to put something on it later on for storage, whatever the case might be, but I want this to be held up. So I tie a rope to one end of the beam and I attach the other end to a wall. Same way. Say the beam has, some weight of 150 newtons. And that's not all. Remember, I'm setting this apparatus up to do something with it. I want to hang something off of it. I want to hang I want to hang a flower pot, maybe I want to hang some exhibit, some sculpture, whatever it is. I'm hanging something here. And whatever I'm hanging at the end of the rod, and this weighs 300 newtons. Well, these are weights, not masses. Keep that in mind. They're not kilograms, they're newtons. So they're forces. They're how much force exerted on the beam. This side is 3 meters. This side is 4 meters. And the length of the string, this is 5 meters. Or maybe I'll just look at this. So the length of the string itself is 5 meters. Now I want to calculate various things. First of all, how much tension should my rope have? Right? I don't want to tie something and have it snap off. So I want to be able to calculate how much tension I need in the rope, or I need the rope to be able to support without snapping off. I would like to be safe. And second, I've stuck a hinge to the wall and everything, but there's a chance that hinge could snap. There's a chance that the plaster could crack. All sorts of things can happen. So I want to be able to estimate what the forces are at the hinge, so that I can do this. I can set this up very safely. So let's draw the other forces. How would the tension act? The tension would act along the string, and then estimating the normal force at the hinge is a tricky thing, because I'm not quite sure what shape or size it is. I'm not quite sure how the contact surface looks. I do know this. I know that regardless of what force is it, what direction it may point in, it will have two components, one along the vertical direction and one along the horizontal direction. So I'm just going to assume the components, and whatever eventual force comes out of it, that's what it is. So I'm going to assume there is some normal component, there is a horizontal component of the normal force, and there's a vertical component of the normal force. I don't know what the surface exactly looks like, but I can say this: every force will have a horizontal and vertical component. So I know I'm not doing anything wrong here. So let me write down the force equations. To write down the force equations, I need to know, first I need to fix my axes. So let's say horizontal towards the right is x, vertical upwards is y. So I have 1, 2, and 3 forces along y, the 150 Newton force, 300 Newton force, and hy. I have hx, which is horizontal. T is somewhere in between. I can't work with T like this, not yet. I need to split up T into its components. so that I can write down the equations along x and y. So let me do that. If I consider this angle to be theta, the angle the string makes with the beam, then sine of theta is opposite over the hypotenuse. So this is 3 over 5. Cosine of theta is the adjacent over hypotenuse, so this is 4 over 5. So what are the components of tension along the x and y directions? Well, one component of tension points upwards, and one component of tension points along the beam on the x, well, along the negative x direction. So this is Ty and this is Tx. Now which of these is the sine and which of these is the cosine component? What I like to do typically is I like to figure out first where the angle is. Alright, so my angle is here between the string and the beam. Now which is the adjacent side to the angle? One is the tension. So the force you're trying to split up is always going to be the hypotenuse, right? Because you're using Pythagoras theorem. So you have to figure out whether Tx is the adjacent side or Tx is the opposite side. In this case, which one is it? Huh? It's the adjacent side to the angle. It's sitting right here. Ty is somewhere up here, right? You could put this Ty here and then it would be opposite. So the x component is going to be the cosine component and the y component is going to be the sine component. All right. So I have this much. So I'm going to set up equations along x and y. So the force equations along x. So I have plus hx points towards the right, and minus tx because tx points towards the left. Of course, it would be a terrible thing if this beam started accelerating. It's going to fall on someone's head and kill them. So clearly, I would like my acceleration to be 0. And along y, I have Ty pointing upwards, positive y is upwards. I have Hy pointing upwards, again positive y is upwards, so plus Ty and plus Hy. And I have the 150 and 300 Newton weights pointing downwards, so minus 150 and minus 300. This is equal to 0. Now, how many unknowns do I have? I don't know tension, and I don't know the normal forces. I don't know the components of the normal forces. I only have two equations. These are the force equations. I need one more equation. I can write that as a torque equation. You see, if it's stable, not only is it not moving upwards, downwards, or back and forth, it's also not spinning, right? So the sum of all forces on it is 0. The sum of all torques on it is also 0. If it were not, then it would be spinning. And you can have a situation where the force is, total force is 0, but the torque is not. I mean, if you're driving, you have a steering wheel, right? When you turn the steering wheel does not fly off. It doesn't go anywhere. It sits there, but it spins. It spins because there's torque. It doesn't fly off because there is no net force. So in this case, luckily, it's not spinning or doing anything very crazy. It's just sitting there. So all the torque must also be equal to 0. Now, just like I have a choice with what x and y axis I can pick, I also have a choice when it comes to torque to pick my axis of rotation. Right? Because if the force is 0, regardless of what x and y I pick, x and y is my choice and I choose it in a way that makes things convenient for me. But if I have a situation where the total force is 0, regardless of what x and y I pick, I am guaranteed that the force is 0. That's what I can say. Same thing with torque. If I have a situation where the total torque is 0, then regardless of what axis of rotation I pick, the torque must be 0. So this gives me a lot of power. I can choose as an axis of rotation. And depending on your situation, you might prefer to pick one over the other. Let's write down a couple of situations. So let's call this point A. Let's call this point A. Let's call this point B. What would happen if you were to write down the torque equation at B? Or let's do it at A. So torque equation about A. Remember, torque is, first I need to figure out where the hinge is. I need to figure out what are the forces acting on the beam. I need to take the force, the distance of the force from the hinge, and I need to figure out that there is at least a component of the force that's perpendicular to the distance from the hinge. Is that okay? Three things I have to keep in mind. First thing, I have to figure out what the forces are. I have to figure out from the hinge itself. If I were to do this about B, I would be measuring distance of the forces from B. Since I'm doing it from A, all the forces I'm going to measure the distance from A. Right? And then I'm going to figure out if there is a component of the force that's perpendicular to that distance. All right, how many forces do I have? I have a bunch of forces. So this is my hinge. So I'm trying to see if the rod can rotate this way. All right. What is the distance of Ty and Tx, or the tension and the 300 Newton force from the hinge? Right now the hinge is A, not B, because I've picked it to be this. What is the distance of T from the point A? How far away from A is it acting? 0. It's acting at A. Right? The rope is tied at A. So does T produce a torque about point A? No. What about the 300 Newton force? How does it act on the point A? Or how far is it from the point A? 0. So again, no torque from the hanging mass. What about Hx? It's acting a distance 4 meters from A. Does Hx have a torque? Imagine this. This is the door, right? So if I want to swing this door open, I have to push. So this is the hinge, and this is the distance from the hinge to my force. I have to push perpendicular to that distance. If I went here and I started pushing towards the hinge, would I ever make the door turn? No. Hx seems to be pushing along the distance. It's pushing directly at the hinge. I'm not going to get a torque from Hx. Hy? I have a rod like this. Imagine this is the hinge and I'm pulling upwards. I'm going to get a torque. Is it clockwise or counterclockwise? Clockwise. And what other forces do I have? I have the 150 Newton force. How far away is it from A? 2 meters. And it's perpendicular to the distance measured from A, right? And is it clockwise or counterclockwise? Very nice. So I'm going to consider all counterclockwise torques to be positive. So now I have confirmed I have only two forces that give rise to a torque. One is Hy, measured distance 4 meters from A, and this is negative because this is a clockwise torque. It tends to pull the beam this way. If I were writing equations about B, things would be different. Again, keep this in mind. And a 150 Newton force that gives rise to a counterclockwise torque situated at 2 meters away from A must be equal to 0. Now I'm going to write the equations and let you solve them in your own time. But to make this point clear, let's do one last thing. Let's write down the torque equation about B. You can do that. I mean, you'll only pick one of the two torque equations. Don't end up writing multiple torque equations and getting too many equations, then you have variables. That is a recipe for disaster. Don't do that. Write one torque equation, but pick a good point or good axis to write the torque equation about. So let's say I write the torque equation about B. Right? All right. What are so this is my hinge now. Well, the natural hinge also for the beam. So I am basically, this is the beam. I'm thinking about in terms of, does it rotate this way? Right? Okay. Does Hy have a torque? No, it acts exactly at the hinge I've chosen, right? Acts exactly at the axis I've chosen. Hx? Hx also should not have a torque. It acts at the point that I've chosen to be the axis of rotation. What about Tx? No, right? Because it points right at the axis. It points directly towards the axis. There's no perpendicular component to Tx. Ty? Ty, yes. Is it a counterclockwise or a clockwise torque? Counterclockwise, because the beam is fixed here. Ty acts upwards, so it's going to try and turn the beam counterclockwise. How far is it from B? 4 meters. What about the 300 Newton weight? Is there a torque from this? Yes, right, because measure the distance from B to the point where the force acts. And you see the 300 Newton force is perpendicular to it. The force is non-zero and the force is perpendicular to that distance. So there is a torque from this 300 Newtons which is hanging with it. What about the 150 Newton force? Yes? You can draw a distance from B to where this force acts. And this force is perpendicular to that distance. So are these clockwise or counterclockwise torques? Imagine a beam, and how do these forces act downwards? So it swings this way. This is a clockwise torque. So you can write down a torque equation about B. So you have a minus 150 acting 2 meters away from the point B, minus 300 acting 4 meters away from the point B, and plus Ty acting 4 meters away from the point B. Again, it's not really spinning, so the torque must be 0. Now you only pick one of these. Only pick one of these. Don't pick multiple torque equations and get yourself in trouble. All right. So, is this okay? I know these problems are hard. I had trouble with them when I started out. So, the only way to be comfortable with them is to pick up as many of these as you can. Just practice all the way through till the end. And after a very stressful, frustrating few hours, you will get it. Now, briefly introduce the concept of rotational work and power. And I'm going to do this by analogy. If I have a block on a surface, assume no friction. Yes. Why is Hy negative for, because it's clockwise. So I'm talking about A, right? So I'm assuming the beam is sitting here. Now, okay, if I didn't tell you that this was a natural hinge for the beam, really if it's just sitting there, there is no way to know where the hinge is. If I were to just keep this, eraser here, can you point out a hinge and tell me that that is a natural hinge for it? Right, it's in equilibrium. If I were to write all the forces on it, they would be zero, all the torques on it would be zero. So for a moment, forget about the fact that B is a hinge, is where I've actually put a physical hinge, and consider the beam trying to rotate about the point A. So Hy would push the beam clockwise, right? Assuming it turns like this. So anything that's clockwise, anything that's counterclockwise, I've chosen to be positive. Anything that's clockwise is then negative, because they're opposing torques. So if I apply a force on this block and moves a certain distance, delta x, the work done is F times delta x. By analogy then, assume I have a pulley that's fixed. I have a rope tied to this pulley, I'm applying a force F, and it rotates a distance delta theta. Right? What would this force do? It would cause the wheel to spin. By that I mean it exerts a torque. Right? There's a torque acting on the wheel. So the work done is tau delta theta. And this is a nice thing because we can do a lot of things analogy, right? So force is the agent that causes an object to speed up or slow down when we're talking linear motion. Torque is the thing that does it for rotational motion. So our analog for displacement or distance traveled in a rotational context is the angle. And because we have the power is Fv in a linear context, what should it be in a rotational context? What is the analog for V in rotation? Omega. So power should be, say that again? Should be tau omega. Well, this is just to introduce you to the notion that this sort of thing does exist in rotational motion also, to keep things consistent. We've been talking about energies without really defining a work done properly, I guess. And what happens, what is the conservation law you get when the sum of all forces is zero on an object, or on a system? What happens when all the forces are zero on a system? What is the conservation law you get? What happens when objects collide? Momentum is conserved, right? You've seen conservation of momentum? Yes? How do you get that momentum is conserved? Because if you have two objects colliding with each other, the only forces that there are exist between those two. You're not doing anything, you're just sitting and observing. You're not applying a force, you're not shaking things. And because all the forces are internal to that system, you're not applying any external force, the momentum of that system must be constant. Therefore, you're able to equate the initial and final momenta to each other. The key thing is that the sum of all external forces is 0 gives you momentum conservation. So if I have the sum of all external torques is 0, what should I have? Should I expect a similar conservation law at least? Right? So there is a notion of angular momentum. So torque is defined as I alpha. So this is again in direct analogy to the linear counterparts. So F is 0, that means so sum of all forces, so that big E is a sigma, it means sum of all forces. So I sum up all the forces on an object, that means, and I get a 0, that's the same thing as if I sum up all the momentum before and after a certain process, it should turn out to be the exact same thing. Similarly, if the sum of all torques is 0, what is the rotational analog for M? What is mass in rotational motion? What is the stand-in? I, it's angular moment, it's moment of inertia. What is the counterpart for V in rotational motion? Omega. Now, where might you have such examples? One very simple example would be if I take we used to have these things when I was a kid in the playgrounds. We used to have these really small merry-go-round type things that kids would jump on and jump off, right? So imagine I have one of that. There's a playground. This thing is, it's spinning with some omega, right? Oh, it's pretty massive, right? It's made of definitely made of metal. Back in my day, at least, it used to be made of metal. I don't know if they've come up with really strong plastics nowadays. But it has a certain amount of size. So it has a certain amount of moment of inertia, right? Now imagine, so this thing is spinning freely. Okay, assume there is no friction at the hinge and everything. Obviously it will slow down after a while. But assume there's no friction or anything. Now, very quickly, a kid jumps on it. Now, this kid is, has a certain mass of his own, situated at a certain distance from the hinge. Say I kid, right? Do you expect the merry-go-round to keep spinning at the same speed? Have you ever jumped onto one of these? Well, you should. Go to a playground, kick some kids off a ride and do this yourself. It's a lot of fun. But think about it. If I have a sliding sort of a box, I jump onto the box, you'd expect the box to slow down, no? Similarly, if I have something spinning, I jump onto it, I expect it to slow down. How is that happening? Well, first and foremost, there is nothing external that there's no motor or anything that's driving this wheel. So nothing is actually physically maintaining its speed. It's just spinning because, we've assumed no friction. Someone set it in motion, and that's how it is. So let's call this some omega initial. Let's call this some, whatever it's spinning with omega final. But my point is, there is no external agent that causes it to keep spinning regardless. What I'm trying to get at is there is no external torque. All right, there is no torque that is acting here. So I can conserve angular momentum. So the initial angular momentum, when it was just the wheel spinning, must be the same as the angular momentum of the spinning wheel later. Plus now the skid is on the right. Now this skid is also spinning. It's stuck to the right, so they both move with the same angular speed. So, because the kid jumped onto the right, and this kid also has some moment of inertia, the final angular speed is going to change. And because this side, the moment of inertia is greater than the moment of inertia on this side, this omega has to be lower to compensate for the increase in I. Here's one example. Another commonly given example is, if you have if you were to imagine yourself skating on ice and holding a couple of weights in each hand, and you started spinning. If you move your hands in, what would happen? Have you seen figure skaters in the Olympics? No. When they spin really fast, are their arms tucked in or their arms spread out? Their arms are typically tucked in. Why? Because closer your arms are to the axis, lower your moment of inertia, higher the speed you can maintain. Again, no one's catching on to this person and putting a motor on her and making her spin. This person is spinning basically with zero external torque. So spread your arms out, you get an increase in moment of inertia, you slow down, pull your arms in, you speed up. Very, very simple physics. Of course, there's a lot more than that. It takes years and years of practice to get that right. But the physics is, if it's any consolation, physics is fairly simple. So you'll see a few problems I expect on the homework. And before we move on to the quiz, I'll just spend a couple of minutes introducing one topic, and then we'll head to the quiz. All right, so you've dealt with springs, right? You've dealt with springs before. You know what happens if you pull on a spring? So we have Hooke's law for that, which works for simple enough cases. If I were to take a spring and if I were to apply a force on it, let's say outwards, the spring would extend a little bit. And this point would, let's say, move here and would get extended by some delta x. Now the spring force is an interesting force. The more you pull on it, the more it stretches, the more the force is. The force is actually proportional to how much you stretch or compress a spring. So if I'm applying a constant force, the spring force at first will probably not resist me too much. And then once I get to a point, it's going to say, well, I'm going to keep increasing, and it's going to say, okay, enough is enough. You're not going to stretch me beyond this point. That's where it ends. So, and how much of, how tight or how stiff or how soft a spring is determined by the spring constant K. And the spring force then is proportional to delta x. And if it's a really stiff spring, it's going to, it's going to have a high value of K. It's not going to allow you to pull it that much. If it's a very soft spring, you can pull it a lot longer than, and then you experience enough resistance. Now, spring force is always restoring. So if I stretch it, it will try to pull me back to the center. If I compress it, it will exert force in the opposite direction. So it's always acting against the direction of stretching or compressing. So all in all, I know my spring force is minus K delta x. This is great. Okay. What would happen if I take the same amount? So let's say I apply a force F, all right, and the spring here, some spring constant K, the spring stretches by some delta x. It stretches a certain distance. Now let's say I have two springs. Both spring constant K. What would happen if I apply the same amount of force F? Would I be able to stretch them the same distance, or would it be more? Would it be less? It would be less, right? Because each of these springs, so now the force backwards has actually doubled because each of these springs is being stretched by the same amount, so the force doubles. So you would notice that actually you only end up going delta x over 2. Or you have equally stiff springs. So in a sense, the number of extendable objects, in a sense, that I'm seeing as I'm pulling away on the spring makes a difference. So it's not just springs that extend. Everyday objects extend. For take any object around you, you'll be able to compress it to some extent. You'll be able to, if you apply force on it, you'll be able to extend it to some extent. So if you take a wire and you apply a force on it, this wire will extend a little bit, let's say delta L. Originally it had some length L0. And it turns out that delta L is proportional to the amount of force I exert on it. Clearly, if I apply more force, it's going to stretch a bit more. Right? Interestingly, it depends on how much it was originally to begin with. And making a bit of a conceptual jump from here to here, more the surface area, less is the extension I have. So it's like, so imagine there are a bunch of strings in parallel here. All right, so more I have surface area, more the number of springs it is accommodating, so the extension goes down proportionally. That's kind of the equation. And there's a proportionality constant that balances this out, so I'm going to rewrite it a little differently. So this is the equation that governs stretching and compressing of wire. So if I apply a certain amount of force on a certain cross-sectional area, the circular area is, so the outer surface area of the cylinder is not counted. It's this cross-sectional area that we are concerned about. That's where the force is acting. That's the area, stretches delta L with an initial length of L0. This quantity is called the stress. This quantity is called the strain. This Y is called the Young's modulus. All right. Again, same analogy. If you have a high Young's modulus, you will have a very stiff wire. For instance, steel has a very high Young's modulus. You can't stretch or compress steel very easily. Rubber, on the other hand, you can. All right, so when Professor Sen comes back, he will continue from here. Let's go on to the quiz.